All right, let's teach you TensorFlow by throwing you in the metaphorical pool and implementing a neural network the hard way, just using TensorFlow's lower level APIs. So remember, to actually open up a notebook from our course materials, you will start by opening up a Anaconda prompt. On Windows, you would do that by going to Anaconda in your Start menu and selecting Anaconda prompt. On Mac or Linux, you could just do this from a terminal prompt. From here, I want you to cd to where you installed the course materials. For me, that's CML course. And then from there, type in Jupyter with a Y, notebook. And that should bring up your favorite web browser with a list of all the notebooks in the course. And I want you to open up the TensorFlow notebook, like so. And you should be seeing this. So let's start by implementing the world's simplest TensorFlow application. We're going to create a TensorFlow graph that just adds up the numbers 1.2, and hopefully it will give us the value 3 as a result. So this is pretty much the most complicated way of adding together 1 plus 2. But it uses TensorFlow, so it's a useful example. We start by importing TensorFlow, and that itself will cause TensorFlow to be initialized, which takes some time. We will then set up two variables called a and b. A will be initialized with the number 1, and b with the number 2. We then construct a graph f that is defined by adding together those two variables a plus b. So remember, nothing has actually happened at this point in the code. We've just defined a graph at this point that says the graph f will combine the variables a plus b with whatever values they happen to have in them. It's not until we actually run a session in TensorFlow with that graph that anything will actually be computed. All right, so before we start a graph, we need to actually initialize its global variables, and we will create a global variables initializer object here called init that will take care of that. Basically, its job is to put the number 1 in A and the number 2 in B. We will then create a TensorFlow session, call it S, and we will actually run the initializer within that session and then call f.eval to actually evaluate the result of that graph that adds together A plus B. So the initializer should put 1 into A and 2 into B, and f.eval should add them together and print out the result. Let's see if it actually works. Shift-Enter. And you can't ignore those warnings. TensorFlow changes very quickly, so it's just warning you that something is going to change again soon. And we did get the value 3 as a result, so that's a good thing, right? 1 plus 2 does equal 3. And this is a very complicated way of doing it, but it is a very scalable way of doing it. And if you want to add together many more numbers, TensorFlow could have done that across your GPU or many GPUs or even many computers with many GPUs on a cluster. That's the power of TensorFlow. But let's do something a little bit more interesting. So let's actually look at handwriting recognition instead as a way of learning TensorFlow. And this is kind of an overused example, but there's a good reason for it. We're using what's called the MNIST dataset, which comes built into TensorFlow itself. So it's very easy to use. We can just dive in and start playing with it. And it's also a fun example to use. It's handwriting recognition. So it's a bunch of images of people trying to write down the numbers 0 through 9. And it's a good test case here because it's pretty simple to work with, pretty simple data. Our job will be to take these images of people trying to write a given number and try to figure out what number they were trying to write. So we are going to create an actual handwriting recognition system here with just a few lines of code, which is kind of cool. So again, we'll import TensorFlow, and we will load up the MNIST dataset here and just call it MNIST for shorthand. We'll call load data on MNIST, which gives us back the training and test data. This comes back as both a set of training images, which are 2D 28 by 28 images that are grayscale images where each value is between 0 and 255, where 0 represents black, 255 represents white, and values in between represent various shades of gray. We also have label data as well, which are just the numbers 0 through 9. So for every image, every 28 by 28 image, we also have a label that indicates what that image is supposed to represent, 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Similarly, we have a test set as well of images and labels too that we can use to evaluate any models that we create. And the way that this works with MNIST is we have 60,000 samples in our training data and 10,000 in the test data. Now, to make things a little bit simpler, we're actually going to flatten these images down into one-dimensional images. Now, there are ways of dealing with two-dimensional images that we'll look at later, but to keep things simple, I just want to use a straight-up multi-level perceptron here, right? And to do that, I just need to feed in a bunch of input neurons at the bottom. So imagine this 1D array of input neurons. We're going to map that to a 1D array of pixels from each image here. So that's why we're flattening these things out into 1D arrays of 784 pixels across. 28 by 28 is 784. We'll do that to both the training images and the test images. And furthermore, we will cast those to floating point values and divide them by 255. That gets the actual image data down into the range 0 to 1 instead, which is a better range for dealing with neural networks. We are also going to convert the format of our label data from the digits 0 through 9 to categorical data. This is going to be what we call one-hot encoded data. So we're going to convert our training labels into one of 10 categories here. Now remember, when we're dealing with a neural network, the output is just going to be a neuron for each category that we're trying to classify things into. And in this case, we have 10 categories that represent the 10 digits 0 through 9. So in order to get a representation of that we can compare against that final output layer, for example, the number 1 would be transformed into this array here, 0, 1, 0, 0, 0, 0, and so forth. Now we start counting at 0, remember, so the value 0 would have a 1 there, but the number 1 would have a 1 there instead. So where that 1 exists within that array represents which number we're actually talking about. It's just a way to map our human readable number into an actual classification instead, because our neural network just knows about classifications. It doesn't know the meaning of, base 10 numbers necessarily. All right, so we've actually massaged our data into a format that's more easily used with a neural network. So let's run this before we forget. And just get a feel of what we're dealing with here, let's write a little display sample function here that just displays some of the training data that we're dealing with so we can get a more intuitive feel of what we're up against. All this function does is print out for a given sample in our training data set what our one-hot encoded categorical label looks like. We will then convert that back to a number by using argmax. That just looks at the largest value within an array and returns its position. So that happens to work nicely for plucking out where that 1 exists in our one-hot encoded value and returning that back as a number. We will then reshape our flattened 784 1D array that represents that image back into a 28 by 28 two-dimensional image, and then use matplotlib's imshow command to plot that as an actual picture. So let's go ahead and run this and use that to display whatever training sample 100 looks like. Shift-Enter. And there you have it. So you can see that the label associated with this training sample is 5. That's supposed to be a 5. And as you can see, we're dealing with some pretty sketchy handwriting here in some cases. So this is not as easy of a task as you might think. And the one-hot coded representation of that 5 looks like this, 0, 1, 2, 3, 4, 5, with a 1 in that 6th position there. All right, so if you want to play with that some more, you can actually substitute it in different numbers for that sample. If you want to see what sample 1000 looks like, for example, you can do that. And it's a 0, then actually looks like a 0. That's not too bad. And play around, get a feel of what these actual images look like. It's always good to have an intuitive feel of what your training data looks like so you can see what sort of issues you might have to deal with and see if you have any bad data that you might have to eliminate as well. MNIST is already cleaned up for you, fortunately, so we don't have to get into all that, data cleaning stuff. So that's your sort of gut level feel of what the training data looks like, and we'll continue on in the next lecture.